Michelle, you may start it.
Okay. Hello, I'm Michelle Davis of the Center for Manufacturing Research at Tennessee Tech University in Cookeville, Tennessee. Welcome to the Spring 2020 Golden Eagle Additively Innovative Virtual Lecture Series. This is the 9th semester we have produced this popular and informative series. The series is hosted by TTU Center for Manufacturing Research and the iMaker Space at TTU. Additive manufacturing is a focus of both entities, and as such, this short virtual lecture series has been planned to highlight the best practices, potential problems, technological advancements, innovations, and scientific contributions in additive manufacturing, with expert talks from various institutions, industries, R&D centers, and laboratories. Today, we are honored to hear from Dr. Oana Ghita, Chair and Professor of Material Science and Manufacturing in the College of Engineering, Mathematics, and Physical Sciences, Academic Lead of Center for Additive Layer Manufacturing at the University of Exeter in the United Kingdom. Her talk is entitled Additive Manufacture with High Temperature Polymers. The speaker will provide her contact information for questions after the presentation is over. Thank you, and I turn the presentation over to Dr. Ghita.
Okay, thank you, Michelle. I'll just share my screen. Hopefully it will work. Oh, I get a host disable attendee screen sharing. I think it's the same we had before. Terry?
Now you can do it.
Okay, great. Okay, just 1 second. Okay, hopefully you can see my screen.
Yes.
Yes, okay.
Go to,
okay.
Right.
Yeah, great. Thank you. Okay, so my name is Oana Ghita. I'm a professor in materials and manufacturing at University of Exeter, and also I lead the Center for Additive Layer Manufacturing in Exeter in UK. So good morning. It's good morning at your end, everyone, and thank you for invitation. So my talk today will be focused on high temperature polymeric additive manufacturing, and more exactly the high temperature powder bed process. This is a key area of research at Exeter. So my talk will provide a bit of background about the university and the Center for Additive Layer Manufacturing, and then few details regarding high temperature polymers. And then I decided that this talk is going to concentrate on the polymeric, so high temperature polymeric powder bed process, which, although it's been around for 10 years, I do not believe that there is a lot of information, a lot is a known area, and definitely not as known as, for example, is the free form fabrication, or as it is known as FDM. So I will concentrate on, for example, describing some of the unique features of the process, some of the differences between the conventional process, and when I talk about conventional, I refer to nylon, and as well about some of the challenges in relation with the materials, and some of the developments, methodologies we developed for optimization, for process optimization. So in terms of the university, so the University of Exeter, so it's situated in the southwest of UK. If you visited UK, so it has its own airport. It's about 2 hours away from London. In terms of according to the Times Higher Education, so 2020 World University Ranking, Exeter is 146 in the world. It's part of the Russell Group, as we call it in UK, so it's the research intensive university. I think one of the unique features of the university is the surrounding. So it's a registered botanical garden. It's described by the Times as the best garden campus in Britain. So it has quite a lot of unique features, and during this time of the year, it's really nice. It's unfortunate we can't take advantage of all this. In terms of the Center for Additive Layer Manufacturing, the Center for Additive Layer Manufacturing is based in the College of Engineering, Math and Physical Sciences, and was set up in 2010. Includes between 10 and 12 postdoctoral research fellows and PhD students. And the unique expertise of the center is high temperature polymers and composites additive manufacturing. So as a group, we look at thermoplastic broadly, but the most intense research is in high temperature area. For this, we have unique capabilities. We have powder bed and extrusion deposition equipment specific for high temperature. For example, we have the EOS P800 system suitable for high temperature. Also the new P810 recently released a year ago or so by EOS. We got various, so we got two systems, FDM systems for high temperature. We also have a lower temperature, and to help us work through optimization or material development, we have a lot of powder and general material characterization equipment, for example, from powder rheology and powder analysis all the way to thermal analysis, mechanical testing, and so on. So in terms of high temperature polymers, there is a wide range of polymers available when it comes to high temperature, but one key family of polymers we've been concentrating on was and is polyaryl ketone, which includes polymers such as PEEK, PEG, PKK, and you see the formulas described in the image. In how they differ, they differ in terms of the number of ether and ketone bonds, and depending on the ratio of the two functional groups, the temperature, the melting temperature and the glass transition temperature is changing. And you can see in the graph the variation in temperature, glass transition and melting you can achieve depending on which grade of polyaryl ketone you investigate. Now you might wonder what is unique about these polymers. They have quite a wide range of unique range and still wide range of characteristics. They are suitable for medical, they are suitable for aerospace, they are suitable for automotive, and for example, oil and gas. And here is a kind of a brief description of some of the key features. For example, they retain their mechanical properties over a wide range of temperatures from -40 to 250. They tolerate high strains. They are a lot better than thermosets in terms of their toughness and fatigue resistance. They are corrosive resistant. So if we talk about, for example, having a highly corrosive environment, for example, a three-phase environment of for example, 100% hydrogen sulfide, gas phase, high pressures and temperatures for a long time, very little variation in properties we can discover, for example, on some of the polymers being tested. Victrex been doing some tests and some interesting studies out there. Light weighting, so they are known. PEEK has low specific gravity and is less than half that of aluminium. It's 70% lighter than metals, while maintaining its equivalent strength and stiffness. For example, 70% lighter than steel, 55% lighter than titanium. Wear resistant, again, high durability in gear applications, and also it's a biomaterial. PEEK has been used, for example, specifically in orthopedic, spinal, and trauma applications for several decades now. In the 1990s, PEEK started to emerge as a thermoplastic to be used as an implant to replace metal implants, again, specifically in orthopedics. Also is radiolucent, so can be used for X-rays, MRIs. The modulus of the material is very close to the bone modulus, and it's resistant to creep and fatigue, suitable for blood, bone, and tissue contact, and also can withstand repeat sterilization. So it's really really suitable for example use as a tool in the medical sector. So so that's kind of set the scene in terms of the specific family of high temperature polymers, polyaryl ether ketones. So moving forward, as I mentioned, we will talk about equipment, and I assume that the audience is familiar with the traditional conventional powder bed process. So I'm going to talk about the features which are different or unique to the high temperature powder bed system. So in addition to the fact that we operate at higher temperatures, so we have temperatures up to 400 degrees, so the entire heated chamber can go up to 400 degrees. The bed has a lot of heating elements embedded into so-called the exchangeable build frame, as you see in the picture. So these help to maintain the powder bed heated and to allow a slow cooling process. Also, the laser sintering steps, they follow the conventional traditional steps, but at the end, the high temperature system has a post-sintering stage. So that is a period of approximately 12 seconds when the heaters, the infrared heaters, are switched on continuously to allow homogeneous temperature to help to create a homogeneous temperature across the bed. Also, because the high temperature range is used, the powder bed can be more susceptible to flow changes. So what we monitor at room temperature and considered as being a good flowing powder, very often when you raise the temperature suitable for the process, the powder it doesn't work anymore. So for this reason, very often the process requires a tempering stage of the powder. So the powder during this stage, the powder is kept at elevated temperature between 200 and 250, depending on the material, for 6 hours and more, which helps to improve the flow. This is due to the fact that many of the particles have such characteristics that make them prone to change. It is, as you will see later, it is harder to control the quality of the powder from the beginning all the way through the end because of the temperature. And also, as the last comment about the high temperature bed, is the size of the build area. So here is an example of you see the values and the size of the build area, the blue rectangles, they explain the size of the build. So it's about 560 millimeters and 700 and also 380. So it's quite a large area compared to some metallic systems, some of the large metallic powder bed systems. But what is unique and different to the high temperature powder bed systems is the fact that they can work in a reduced mode, and you see the smaller sizes within the larger bed. So you might wonder how that is possible. It's and again a unique feature of this specific range of polymers. They have the capacity to self-support themselves. So so the powder doesn't need a special container, will just stop at the end without having to just to self-support itself, as you see in the image in the slide. So a few mechanical adjustments are necessary to change the internal structure of the double blade recorder. And also the feeder beam, in order to match the geometry of the new recorder, and some modification in the orientation of the infrared heaters. But overall, the system can operate into reduced mode with very little modification with a self-supporting powder. Sometimes the infrared heaters have to be moved slightly to allow still a good temperature environment. So the angle of the build mode, where the infrared heaters are at 41 degrees, they have to be changed to 45 degrees. So these are unique features available only to high temperature powder beds, as far as I'm aware, and quite unique when we talk about these reduced mode chambers, where the powder is self-supporting and is able to build in a smaller area. If you think about some of these polymers, they are highly expensive, and having to build components or even parts, small parts, in such a large bed will require a lot of powder. The fact that we can operate in a reduced mode without changing the performance of the system, the temperature gradients and everything else, it's quite unique and benefic in the same time. So this completes the discussion about the equipment, and moves to the next stage of the discussion, which is the powder. So when the system has been developed, some of these powder bed systems been developed. So the first one in 2009, this came available with one powder, and that was a PEG powder. It was a good powder, but had some faults in a way that once used, it cannot be reused. So the temperature was affecting so much the powder that was not, the powder could not be reused, and that was a problem. A very big problem in manufacturing, as the cost of the components were extremely high. So that was with the fact that the powder was degrading, really, and the cost of the material was very high. So since 2010, when the center was set up and we invested into high temperature additive manufacturing, a lot of our work and research was on development of powders, on working with material manufacturers to develop the right grades of polymeric, high temperature polymeric powders. So that's is still ongoing. But a lot of progress has been made, and a lot of understanding of the challenges of high temperature polymers came through that. So here is an example of some of the powders. You have nylon in the picture, which is seen as a benchmark as far as we are concerned. So we take that as a model in terms of the particle size distribution and the shape, quality of the morphology of the powder. And then you see in the other three images various grades of powders, some of them commercially available, such as HP3 PEC, and this is the first powder which I was talking about, which has been and still available on the market, although with this, the fact that you need to be aware that it cannot be recycled, so that is it's a downfall to the material. And you see also PKK and peak powders, and you see the morphology quite clearly, the morphology of some of these polymeric powders. So they are very rough, they are porous in comparison with nylon. Of course, this will influence significantly the flow and the behavior at temperature. So for us, as I said, a significant amount of work was carried out to try to understand, for example, the shrinkage of the powder bed during laser sintering, as we know that, for example, powder and the shrinkage will be affected by crystallization of the polymer, by the powder bed, and also the thermal contraction of the material. So because the powder is so rough and porous, the bulk density is of the powder bed is low, and therefore this when elevated at high temperatures, all these shrinkage effects are becoming more pronounced. So lots of our work and publications are related with this type of investigations. For example, here, I thought this is a good illustration of some of the changes which could take place during when the powder is exposed to high temperatures. The images show the change in particle shape as a function of temperature. So these were recorded with the help of a hot stage and camera. So the roughness of the particle was recorded through the perimeter measurements, and we can monitor how those are changing. The black represents the room temperature, so the original particle as it is at the room temperature, and then as the temperature is increasing, you see the shape of the particle change. So if we compare, for example, PEC HP3 particles, this is the commercially available material, which is definitely better in comparison with all the other grades under development. You can see that the shape there is no significant change because the shape is relatively kind of round and not so porous, but and rough. But if we look at the other grades, the capstone 6000 particle, we can see how the particle is changing in the background, so we can see the light gray. Similarly, if we look at the two particles coming together, so trying to monitor the neck growth, we can see the changes, the drastic changes which take place during the heating of the particles. One interesting area, and study for us was trying, and unique as far as we could see, this was not looked at before, was trying to assess individual particle behavior as a pre-step to neck growth. Considering that they are so porous and so rough, it is important to understand how individual particles will behave when exposed to such temperatures. So when we did that, we noticed that there is some shrinkage taking place with some of these particles prior to melting. So if we look at the graph, so the T minus 4 represents the melting temperature, and before and after is as the temperature is increasing. So we can see that the melt, its shrinkage happens before it's actually then the particles start to expand again. So this was related with a combination of factors, porosity, but not so much porosity, but more to do with the physicochemical behavior of the polymer, and the we believe is an elastic deformation before the melt, and recovery from this deformation during just prior to the melt. So a lot of studies, so we've done a huge amount of work trying to understand how these particles are changing, and maybe it's I would say it's unique to high temperatures because of the concerns and the issues of powder morphology. These are not available in nylon because nylon, the method of fabrication of nylon powder is very different than it is for these high temperature polymers. These high polymers are produced as very large particles, about 2-3 millimeters in size, which are then milled. So the process of achieving powder for high temperature is milling. And it's very difficult because particles are very tough if they are dense, and it's very, very difficult to mill them. In order to make the milling more successful, the powder has to be, these particles have to be relatively porous. If they are relatively porous, then we introduce this roughness in the particles, which make them difficult to flow. And obviously then affects the sintering process as well. So because of that, a lot of the work we've been doing at Exeter in development of some of these materials was into understanding the distribution, the flow, the particle shapes, characteristics, sometimes as a function of milling, sometimes as a function of grade of polymer. Viscosity will play a role as well in some of these results. So this is a challenge, is ongoing challenge to try to create the right powder for the right high temperature polymeric powder for powder bed processes. Getting the combination of characteristics, as I said, in terms of flow, morphology of the particle and distribution is extremely challenging. And it's an ongoing area. We've been working with various materials manufacturing, trying to support them to get the right performance from some of these materials. So this concludes the discussion about powder, about polymeric powders. And then I'll talk about some of our interesting findings when it comes to laser sintering parameters and optimization process. When it comes to defining the optimizing a process and defining, for example, a powder bed temperature for a new material, the traditional methods involve a lot of trial and error and a lot of powder being used. But what we were trying to do is to try to develop a method based on thermal analysis, where the material used is in small quantities, is a faster method, and quite repeatable and robust. This method we discovered that is valid only for high temperature polymers, cannot be applied for example, for nylon grades or lower temperature polymers. So this is a unique feature of high temperature materials, and in this case of polyaryl ether ketones. We checked it only for this range of polymers. What we noticed is that that the operating temperature, bed temperature of the high temperature polymers is well within the melting peak of a polymer. So here we got it's a part of the DSC trace, differential scanning calorimetry. So it's a method which allows us to understand the temperature at which a polymer melts and then crystallizes. So the blue line shows us the melting of HP3, in this case PEG, so polyether ketone. So the peak of melting is approximately 370 degrees. The onset is about 320. So what we noticed is that if we through trial and error, and also because this is a commercial grade information was available in terms of what is the bed temperature we should operate the system at with this specific powder. If we compared the trace with the temperatures we know of melting with the actual powder bed temperature, we discover that we are well within the melting melting region of the melting peak. So that was strange, and then we thought, well, what's going on here? So let's try to check with other polymers and try to define, to see whether we can find a method to investigate that. So one obvious thought we got was to create the first derivative of the original curve, of the melting curve. So the red is the first derivative, so you can see the minimum and the maximum. So that will tell us the points of fastest change during the melting process. So what we noticed is that if we, for example, compare the temperature at which we know that the system operates, for example, PEG, you can see on the picture, PEG HP3, and for example for PEEK, 450 PF of Victrex grade, that the temperature at which we operate the system is well within the melting peak, and actually it's spot on the minimum point of the first derivative. So we try to check this method, whether this makes, as I mentioned, whether this method works for nylons, and discover that it doesn't follow the same trend. So in the picture on the left, you see the PA 2200 virgin, so that is a PA 12, so it's a nylon 12 grade. We included virgin and also 50-50 used in virgin. So if we look at the temperature, operating temperature, bed temperature is 169, is well outside the melting peak. Also, if we looked at PA 11, so this is nylon 11, on the right, top on the right, we can see again that we operated 185, but still outside the melting peak. But if we look at the two polyaryl ether ketone grades, PEG and PEEK, we can see that we are spot on. The bed temperature it's well within the melting peak and is actually spot on the minimum of the first derivative. So that was an interesting finding. We then checked it also on a more recent grade. This is on a PKK, Capstan 600. And as you can see from the picture, again, the first derivative, it's actually spot on. 290 degrees is the temperature at which the bed operates. So here in this table, you can see the minimum of the first derivative, 366 for HP3, and the bed temperature at which we operated based on trial and error. So we wanted to check that they match, is 365 for 152 grades of peak, 341, 338. So you see the differences there are some small changes, but that's not surprising, and there will be some variation. And the last one is PKK. I was showing the image of 290, and actually the part bed temperature we currently operate is 292. So very, very close very, very close in terms of temperatures. So this seems to work very well for all polyaryl ether ketones, but not for nylons, as shown. I'll come back here just to explain that in the images we have on the right, what we try to do, just to try to understand a bit better, we know that if the bed temperature is within the melting peak for the polyaryl ether ketones, at the end the powder is still is a cake, but is still usable. For nylon, we know that if we would operate within the peak, we would consolidate the powder. So at the end of a DSC experiment, so we opened the pan and we looked outside to look at the powder to try to see whether that's still the case. So in the case of nylon, as you can see in the image, we were able to break down the powder at 185, at 180, but 200, which would be the minimum point of the first derivative, the powder was solid. There was a block, was impossible to actually break down. Where in the case of the peak material, when we are at 332, which was the temperature well within, was at the minimum, was the material was still in the powder form, and when we reached 340, which was almost at the melting point, only then you could see a consolidation of the powder. So this is a unique feature, a very interesting feature, which we came across during our study. And this brings me to an end of my presentation, and hopefully gave you a bit of flavor of the kind of investigation and work we do at Exeter. The systems are different, the way the polymers behave some of the polymers are different. The analysis we do is different. I think that in the literature there is less information on, for example, on the powder flow and morphology, but that is very important for some of the work we do. And the polymer seems to have unique and slightly different characteristics than what we are used with when we talk about powder bed processes and nylon, for example. Thank you.